Okay, welcome to our second video in the pressure series. This is talking about pressure in a liquid today, or we could say fluids, but in particular we're going to talk about liquids. What's the aims? Linking pressure and depth using a formula and applying some ideas of pressure to floating and to deep sea creatures. So first up, quite a strange picture I know to choose. If you have a look at these fish, what on earth has happened? Do fish have tongues? I don't think so. So what's happened here then? The clue is that these are both deep sea fish, so they're used to living, their natural habitat is at the bottom of significantly deep water. So something's happened and they've been brought to the surface. So what on earth has happened? For a bit of a clue, have a look at their eyes. And we know they haven't got tongues, so it's as if something's come out of their mouths. So I wonder what's caused this. Well, let's have 5 minutes talking through the lesson and we'll come back to these pictures at the very end. Sorry if they're making you feel a little bit squeamish. So here we go then, the classic demo of how pressure changes with depth. This is a can full of water with 3 holes in the side. The holes are at different depths and you fill up with water and you take the plugs out of the holes and you have a look at the water coming out, and you can see from this simple picture the water at the top appears to come out with less vigour than the water at the bottom. So we would say the water at the bottom is under a higher pressure than the water at the top. We know this because the force appears to be greater at the bottom. So we know from our last lesson that pressure is equal to force divided by area. So this idea of a greater force must mean that there seems to be a higher pressure with depth. Okay, so you may have seen this in the classroom. If not, you can do it with a 2-litre bottle of pop and put some holes in and fill it up with water and you'll see the effect yourself. Okay, so from this, our very basic or first stop conclusions are the holes in the can are all the same size. When the can is filled with water, the pressure at the bottom is greater. This is because the water is deeper. This means that the water spurting out the hole at the bottom comes out faster because there is a greater force on it. And remember, because the holes are the same size, we know that the area of the holes will be the same. So using the idea from last lesson, pressure is force divided by area. So how would this affect the construction of a dam? If you've seen dams or you might have walked across the top of them, this is sort of what a dam looks like from a side profile. You only would see the top, but underneath, if you look down into the construction of the dam, then the wall at the base of the dam, where the water is the deepest, has to be thicker. The wall at the top can be thinner, and this is because there is a lower pressure at the top than there is at the bottom of the dam. So because there's a high pressure, and remember in a liquid, pressure acts at a surface, pressure will be acting at right angles to that surface. So the pressure on the thick wall will be pushing it outwards, the pressure on the bottom's pushing it downwards. And because the water's deeper, we would need a thicker wall at the base of the dam. So the formula, which you are given this formula on the physics formula sheet, but I'm sure you could work it out yourself. What have we said so far? In a liquid, the pressure is due, or the pressure is exerted due to the liquid that's above you. So the deeper you are, the more liquid there is above you, so therefore the greater the pressure. Now the denser the liquid, remember, density is to do with the number of particles in a given volume. Density is mass divided by volume, remember. So the denser the liquid will mean, literally, there are more particles above you in a denser liquid than if you were in a less dense liquid. So there must be the pressure, the formula must, first of all, link to depth, and secondly, it must link to density. But so we've said pressure must depend on density and the height or the amount of liquid above you. But what else? Well, think, what is pulling this liquid down that's above you? And the answer is quite simply gravity. So our pressure idea must also be linked to gravity. So we have the formula that pressure is equal to the height of the water that you're under, or the liquid that you're under, multiplied by this symbol here in the middle, which looks a bit like a P, but it's actually the Greek letter rho, and this is our symbol for density, multiplied by gravity. So pressure is height times density times gravity. Worth considering the units. We know from last time the units for pressure are pascals. Height we measure in meters. Density is in kilogram per meters cubed. Remember, it's mass divided by volume, and our gravitational field strength is normally given as newtons per kilogram, and it's normally at GCSE given as 10 newtons per kilogram, although it might be given as 9.8 sometimes. But remember, this is on the data sheet, so you don't need to learn this equation. Okay, let's try and trick you. So looking at this picture, which letter is under the greatest pressure? A, B, C or D or E, so which blue dot? Have a look at the formula and think to yourself, okay, pressure depends on height, density and gravity. All of this lot is under the same gravity, all of this lot is under the same density, so there's only one thing that really can affect it, and that's the height. Now, all of these are under the same height of water. If you measured the depth of water above each of the blue dots, then all of them are the same height, which is this line. This is the only one that might be slightly confusing. You don't measure the height at an angle. You literally measure the vertical height of the water. So it's a trick. They are all under the same pressure because H, density and G are all the same for the dots A to E. Okay, and to finish, nearly to finish, let's do some questions. We've got 5 questions. A diver dives to 30 metres. Seawater density is 1029 kilograms per metres cubed. What pressure? So using our formula, it's fairly straightforward. Height times density times gravity. 30 times 1029 times 10 gives us an answer of 308,700 pascals. That could be written as 309 kilopascals, rounded up to the nearest kilopascal. A world record was set when Amit Gabor dived to a depth of 332 metres. What pressure was he under? So again, height times density times gravitational field strength. Here I've got 3,416,280 pascals. So again, this could be 3,416 kilopascals. Explain why the pressure Amit experienced was much greater than the diver in question 1. Well, the biggest difference, or the only difference, density is the same, gravity is the same, it's the height. Look at that, the height is pretty much 10 times deeper. So that 10 times increase in depth gives a pressure increase of 10 times. Okay, a diver in fresh water where the density is 1,000 kilograms per meters cubed, remember this isn't seawater now, it's fresh water, experiences a pressure of 483 kilopascals. What depth did she dive to? Well, to do this we need to rearrange the formula. So looking at the formula, we can say that pressure divided by density times gravity will give our height. So pressure divided by density times gravity. So pressure is 483,000, remember kilopascals, divided by 1,000 times 10 gives you a depth of 48.3 metres. And finally, a very keen learner diver has only an extremely muddy lake to practice in. He managed to get to 8.5 metres and experience pressure of 147.05 kilopascals. What was the density of the mud? So first of all, let's work out the density of the water at this depth. So if we were density, rearranging this again, density will take height, so it's pressure divided by height times gravity. So take the H and the G over. Pressure is equal to divided by height or depth times gravity. Put in our numbers, 147,050 pascals. I've converted this into pascals. Divided by 8.5 times 10 gives us a density of 1,730 kilograms per meters cubed. Now this question is slightly tricky because how do I know that's the density of the mud? Well, at the point where the mud would sink, the mud is denser than the water. So if the water has a density at this depth of that, then the density of the mud must be equal to or slightly greater than 1,730 kilograms per meters cubed. Okay, a little bit on pressure and floating. If you look at this box, if we've got a box, a cuboid submerged in a tank of water, let's have a think. There is a difference in depth between the top and the bottom surface. So the top surface is at H1, the bottom surface is at a depth of H2. So what does this mean in terms of pressure? Well, if you think about it, the pressure at the bottom will be greater than the pressure at the top. And remember, pressure acts at right angles to any surface. So there is going to be a force on the bottom which is greater than the force on the top. The force on the top will act downwards, the force on the bottom will act upwards. This will mean there is more force on the bottom than the top, and this difference in pressure is called upthrust, or the buoyancy force. So what we're saying is that this will float, okay? Well, it will only float, forgive me, if this difference in force is greater than the weight. So whatever this cuboid block is, If whatever weight it has, if this upwards force is more than the weight, it will rise up. If it's less than the weight, the block will still sink. If it's exactly the same as the weight, it will not move, it will just remain stationary in the water. So this is another way you can consider floating. Okay, and an object will float if the upthrust on it, and the upthrust is the difference in the pressure between the top and the bottom, and it will float if the upthrust on it is greater than the weight. So finally, back to the horrible pictures of the fish. So can we now explain? So we did say that they're deep sea fish. Their bodies have been used to, or their natural habitat is under a significant high pressure on the outside of their body. Obviously they've been brought to the surface and the pressure has significantly reduced. They're now under just atmospheric pressure, which we're going to talk about in the next video. So because there's a significant decrease in pressure, well, their body's used to a higher pressure on its surface. Now we've removed that pressure. What's happened is that their body is sort of or not turned inside out, but their eyes have popped out because the pressure no longer holds them in, and the pressure would have been transferred into their body down their throat, and because that pressure is now gone, literally the esophagus, or something called a swim bladder, has expanded and come out of their mouths due to this decrease in pressure. So quite a strange sight, but hopefully now you can explain it in terms of the idea of pressure in a liquid.